Hello, my name is Steven Silva, and in this presentation I will show you the research project called Autonomous Intelligent Navigation for Mobile Robots in Closed Environments. This project was made in collaboration of a research center from Spain called CITES. This presentation is also for the International Conference on Applied Technologies Latacunga. As an agenda, what we have is the introduction, methodology, results, and discussion, and for the last part, conclusions and future works. This research project is based on AMR, which means Autonomous Mobile Robot. And as a definition of them, what we have is that it is a robot that is capable of knowing and understanding its environment while moving without being controlled, monitored, or supervised directly by an operator. This means that it is a mobile platform that can be programmed to go from one point to another while making its own trajectory and planning its own movements. This also includes avoiding certain obstacles like people or certain objects like chairs. In order to do that, most AMRs rely on what is called SLAM navigation. However, to do SLAM navigation, first a mapping process needs to be done, in which a map is created and then given to the robot so that it can know its environment, its surroundings, and plan its trajectory to go from one place to another. Nowadays, there are several ROS packages for mapping, but each of them have different capabilities. This means that some of them, for example, are made for indoors mapping and some of them for outdoors mapping, as well as the hardware that they use. Some of them use, for example, depth cameras, and some of them use other sensors like LiDARs. Even some of them use ultrasonic sensors. As said before, more than 10 mapping packages have been stated till today, but as seen from past studies, the one that shows the best performance is Cartographer ROS. This could be for the reason that while it makes the mapping process, it creates submaps that give a better result to the final map. This means that the resulting map gets optimized while it makes the map continuously. Now, there are ways to know whether a map is good or bad, and if it can be used or is efficient for navigation. For example, if the resulting map has an enclosed area that shouldn't be enclosed, it is called as a bad quality map, because the robot could get stuck in this area and not go to a desired point or area in the map. Now, in this research project, we are looking forward to test Cartographer ROS to whether it can or not be used in real indoors environment, even with cheap sensors like the RP LiDAR A1. We had so in order to get to know the quality of the map provided by the cartographer node, simulation and experimental tests were needed. For the simulation tests, we had to do an environment setup. We had to decide a place, which is the one that you can see in the picture, a living room, and then 3D design it in a software, which the one that we used was Onshape. As you can see there in the right image, there is the chairs, the doors, there are some of the sofas, and even a TV with its support. Once the 3D design of the living room was made and finished, we exported it to one of the tools that ROS has called Gazebo with another tool called Onshape2Robot, which is a Python library that lets us do it, basically convert an Onshape design to an SDF format or even a URDF format, which is what is used for simulations in ROS and Gazebo. As you can see in the right part, there is the simulated environment. As you can see, there are the chairs and the sofas in which we run all the mapping process. Now, for the robot setup, there was no simulated robot for the Arlo robot platform that we were using, so we used, as already stated, simulated robot like the Turtlebot 3 Burger, which was really like the one we used. as you can see in the right picture there. And as you can see in the graph, this is the graph that we used in order to make the mapping process. As you can see, there is the cartographer node, which also publishes the submaps to the cartographer occupancy grid node, which publishes maps, the map basically, which is what is used for the navigation process like move base. Also, you can see there is the node Gazebo, and this is all the implementation of the simulated setup. Also including the Turtlebot 3, which is made by the Robot State publisher. For the part of the experimental one, we had to include some other stuff. For example, an ESP32 and a MicroPython. There is a MicroPython library called Roserial, which lets us and helps us connect the ESP32 to the ROS master in order to be able to publish encoders values, and also take the velocities that are given in order to map and even for the navigation processes. As you can see in the right part, there is the page from PyPy for the MicroPython Roserial package. And as you can see in the left part, there is the graph where you can already see the serial node which comes from Roserial, and it publishes R-wheel and L-wheel, which are the encoder's position, and gets the velocity targets. This was needed in order to control the DHB10 driver to control the DC motors from the platform. This was only needed for the experimental part of the tests. And so here we are with the results from the simulated and experimental processes. As you can see, in the process or in the result of the simulated environment, the map seems to be really neat. The walls are really neat. You can see there are no holes in it. For example, we can find a hole here. However, it is pretty small, so it's not going to be really harmful for the navigation. We can also see here there are some failures from the map, but this is reasonable. And basically this error that you can see here is because here was a sofa and the LiDAR couldn't, basically the LiDAR, it is impossible for it to get all this area or to sense all this area. So it is mostly an environment or hardware limitation. Apart from that, you can see there are no enclosed areas and that the corners of the map are really well made. It is really well defined. Now, the same happens here, which here was another sofa, so it is reasonable that this is going to happen, and this was predicted. But it doesn't show any problem to the navigation, or it won't show any problem to the navigation. Even if we wanted to go, for example, to this place here, then the robot will know that it can't go there since there will be no trajectory. And because this area over here will be really small for it to go to that place. Now for the experimental part, we can see that it is not as good as a simulated one. For example, in this part here, we can see the wall is really well made. However, in this other part, we can see that it is not that much defined. It has some spikes and that it is a little bit wobbly. However, this could be because of the LiDAR and vibrations in the platform. Also, we have the same errors that we got in the simulated one. For example, as you can see here was the sofa, and this is an error from the map, which was also made because of an environment or hardware limitation. It is impossible for the LiDAR to sense this wall over here and map it. As you can see here, for example, we have some differences in the walls, which is also because here was a kind of a carpet, let's say. The biggest issue that we can see in the experimental result is over here. Basically, here was a glass a glass door. However, the lidar and the way the lidar works is that if you put the lidar in front of a glass door, it's not going to sense it. So this is reasonable to have gotten this part over here, which corresponds to the backyard of the house. Um, let's see. And apart from that, we also have these errors over here, which were because of certain gaps between the door and the walls. So it is reasonable that this was going to happen. But mostly all of the errors that you can see from the map are basically because of hardware and environment limitations. For example, the glass door. If here was not a glass door, or we had another sensor that could be using, let's say, sound waves, we could have seen this part of the environment. At last but not least, we have the conclusions and future works. As conclusions, we have that cartographer Ross is able to provide a really well-made map, even when not using the most expensive hardware resources. As you could see in the results of the map gotten from the experimental test, it was really good compared to the simulated one. Every wall was mapped with no we got holes and some certain errors in some parts of the map. However, they were reasonable and they were hardware limited. Considering where we were using pretty cheap hardware, for example, the RP LiDAR A1 is about $100, it was a really, really nice result. Apart from the simulated test in which ideal that LiDAR is used. Every every sensor in the experiment in the simulated test is ideal. Maps are not of the same quality, but that doesn't mean the experimental solution can't be used, nor that it can compete with the simulated results. As you could see in the experimental part, in the experimental result, there were no obstacles or there weren't any obstruction that could not let the robot to navigate through all the area. So it can easily used for navigation. There were certain errors, for example, the gaps and that the glass door was not sensed and not mapped, but as said before, that is hardware limited. Finally, such good performance is because this SLAM method works with submaps while it goes through the mapping process. This is because Cartographer-Ross algorithm creates submaps to create the final map, the resulting one. Meaning that if the sensor or let's say the robot doesn't map the environment in a part really well, afterwards it can be optimized with any submap that the algorithm continues creating and then merging to create a good quality resulting one, a good quality resulting map. As future works, what we are planning to continue working with is now developing tests to test cartographer ROS for 3D SLAM. We are trying to implement some Intel sensors in order to create 3D maps and giving it an application and implement it in hospitals where the robot could disinfect several rooms while navigating by itself room by room and using UV lights. As we have seen today, this is a really good application in terms of COVID-19. I hope you really liked my presentations and thank you for your attention. I will be glad to answer any question that is made to me. Thank you.